Hello dear students, I welcome all of you to lecture 10 of topology of matrix spaces, unit first matrix spaces. In today's lecture, we study open sets of matrix space and solve some problems on matrix open set of matrix space. Open sets of matrix space. Definition: order pair HD be a matrix space. Let capital G subset of X is said to be an open set for every small p belong to G. There exists a positive real number r greater than 0 such that open ball about small p with radius r is contained in G. Okay, this is definition of open sets of matrix space. Let HD be a matrix space. Let G is subset of this X is said to be an open set for every P belong to G. P is point in set G. There exists a positive real number small r greater than 0 such that open ball about point P with radius r is contained in G. This is the definition of open set of matrix space. Remark: empty set phi and whole set X are open sets in X. This is because for every small p, there exists small r greater than 0 such that open ball about point P with radius r is containing empty set phi. This is trivial, is automatically true as empty set phi does not contain any point. For every p belong to X, open ball about this p with radius r is again contained in X. This implies that capital X is an open set. Thus, for every matrix space has two subsets, has two open subsets, empty set phi and whole set X. Okay. For every matrix space, empty set phi and itself set X is an open set. Examples of open sets. Example first. Let capital X is equal to set of reals R. D is equal to standard metric let capital A is equal to open interval AB be an open interval then capital A is an open set. Proof or solution. This is a real line. Here point A, point B. This is an AB is an open interval. Suppose there is a point X in between open interval AB. Let small x belong to open interval AB be any arbitrary point in open interval AB. Since D is an standard metric, let small r is equal to minimum of set modulus of A minus x and modulus of x minus b. This is R is equal to minimum of set x minus a comma b minus b minus x, since as a is less than x less than b, therefore x minus is a positive number and b minus x is also positive number because x is in between a and b. Okay. We will prove that open ball about x with radius r is contained in open interval AB is equal to set A. Here we have to show that open ball about this x with radius r is contained in set AB. That is, we have to say that, show that if r is in between this, then okay. Open ball about x with radius r is equal to open interval x minus r comma x plus r. Okay, open ball about x with radius r is equal to open interval x minus r x plus r. Let y belong to open ball about x with radius r is equal to open interval x minus r to x plus r. This implies that x minus r is in less than y less than x plus r. Y is in between this interval x minus r to x plus r. If r is between r is less than or equal to x minus a, this implies that x minus r is greater or equal a, and if r is less than or equal to b minus x, this implies that x plus r is greater or equal b. A, therefore a is less than or equal to x minus r is less than y is less equal x plus r is equal to b. This implies that a is less than y less than b. This implies that y belong to open interval AB. Thus y belong to open ball about x with radius r is equal to open interval x minus r to x plus r, implies that y belong to open interval AB. This implies that open interval x minus r to x plus r contained in A, capital A, is equal to open interval AB. Since the point X is an arbitrary point, we get capital A is an open set. This is the solution. Example 2. Let X is equal to R2 is equal to R cross R and D is an Euclidean metric. Let capital G is equal to set of order pair x1, x2 such that x1 plus x2 is less than 4, then capital G is open in X. In this problem, X is R2 space and D is Euclidean metric depend on this X. Let G is equal to set of order pair x1, x2 such that x1 plus x2 is less than 4. Then we have to show that G is an open set in X. Solution. Geometrically, we can sketch the region representing G. First we sketch the straight line x1 plus x2 is equal to 4. x1 plus x2 is equal to 4 if x2 is equal to 0. This implies that x1 is equal to 4. Therefore we get point 4 0. If x1 is equal to 0, this implies that x2 is equal to 4. Thus we get point 0 4. We draw this line in xy plane. This is x1 axis and this is x2 axis. This is point 0, 1, 2, 3 and 4. Here is point 1, 2, 3 and 4. Okay. Then point 4 0 is here. This is a point 4 0 and here is point 0. Okay, we draw a line. This is line x1 plus x2 is equal to 4 and our x1 plus x2 is less equal 4. Therefore our region is lying in these sides. Okay, our region is lying in this side below the line x1 plus x2 plus x1 plus x2 is equal to 4. This is a sketch of or geometrical figure of set G. Okay. the straight line divides the plane R2 into 2 points one containing origin and other not containing origin. Okay, our straight line divides the plane in R2 into 2 points. One is below the line which contain origin and other is upper side which is not contain the origin. Substituting x1 equal to 0, x2 equal to 0, in x1 plus x2 less than 4, we get